All right. Okay. Hello, everyone. Um, Sorry, I'm starting a bit late. Welcome back to your Comp 335 tutorial. This is your fourth tutorial, as you know. So today what we'll be covering is we're first going to look at something that you already saw in the lecture, which is when you take an FA, so either an NFA or a DFA, and then you convert that to a regular expression. And then the second part of the tutorial is going to be about introducing grammars. Okay, so FAs to regular expressions. So you're given some FA, so an NFA or a DFA, and you want to convert that to the regular expression, the equivalent regular expression that denotes the same language that's accepted by this machine. So how are you going to do that? Well, as you already saw in the lecture, there's this idea of a general transition graph that we introduced specifically for this purpose. And the idea is that a general transition graph is exactly like a regular kind of transition graph, but instead of having symbols as the labels for its edges, it has a regular expression. So here, the edge that goes from Q1 to Q2 is a regular expression that's B or lambda. So in other words, it recognizes either the symbol B or the symbol lambda. Okay, so that's the main idea. That's we're going to try to utilize a general transition graph in the following slides. Okay, so the first thing that you need to know when you're trying to convert an FA, here we wrote in this. Oh, sorry, my pen stopped working. So let me just talk. So here we wrote NFA, but it could have just as easily been a DFA, because as you know, a DFA, okay, a DFA is also a form of NFA. But essentially what we need to do when we're taking a general transition graph and converting it to a regular expression is that we need to sort of get rid of all our intermediate states so that we only have one initial state and one final state. So the goal that you're kind of going towards in this algorithm is you want to get something that looks like this guy, okay, where you have some regular expression that goes onto your initial state, the same thing on your final state, and you have transitions from Qi to Qj back and forth, okay? And the idea here is if you have this form of general transition graph, then it's actually quite, well, it should be a bit clearer to see what the regular expression that corresponds to this guy is. And that's because in an FA, what you're going towards is you're going towards trying to accept any string that ends up in your final state. And so you can just map that into a regular expression by saying, well, if you start in your initial state Qi, right, then to go to Qj, what you could do is you could read a bunch of RIIs. So you can stay in Qi a bunch of times. And then you can decide at some point to go to Qj, right, using Rij. So Ij just means that you go from Qi to Qj. That's the notation here. So you go from Qi to Qj with Rij. So at this point, you're already in your final state. So you could stop, but the other thing you could do is you could loop a bunch of times here and then say, okay, I'm going to go back to my initial state, loop a bunch of times here, and then go back to my final state. And then you're still going to end up in your final state. So you still need to account for that transition to say that you're ending up in your final state. So what that kind of translates to in terms of regular expressions is after this Rij, so once I'm here, I can either stay in Qj a bunch of times with Rjj, or I can go from Qj to Ri with Rji, then stay in Qi a bunch of times with Rii. So I stay in there a bunch of times and then come back to qj with rij. Okay, and so because I can do this a bunch of times, I'm going to put a star here. Okay, and so notice it would have also been fine, like you could have also put in a, whoops, you could have also put in a star here. Okay, but this star kind of does the same job as saying you can get rjj a bunch of times. Okay, so but you can, if it kind of makes you see it better, you can keep the star here, but really it's not necessary, and this is usually the form that we end up having. So this is something that is already in your lecture slides. It's just kind of a reminder. Okay, so what is then the procedure of you're taking an NFA and you want to convert that to a regular expression? Well, the first thing you need to do is you need to take your NFA and convert it to a general transition graph. So in other words, any edge you have is converted to a regular expression. Okay, but what you need to make sure in this algorithm is that you have a single final state. Okay, and how do you make sure that you have a single final state? So suppose you have this machine here and it has a couple of final states. How am I going to make it have a single final state? Well, I can just use these nice convenient lambda transitions, right? I use a lambda transition here, lambda transition here, a lambda transition here, and all of these go to a single final state, and now I can make all of these non-final states. So clearly you can see that it's equivalent because if you end up here, then you don't have to sort of give anything else. You can just use the lambda for free to go to your final state. Okay, so you can technically end your string here, but then just use the lambda to reach the final state. So that's how you can make sure that there's a one final state. Okay, and so the idea is you're going to try to get to a general transition graph that looks like this. Okay, so to do that, so I'm going to show you a very busy slide, but don't get scared. To do that, if you have an intermediate state, right? So in this case, this is your intermediate state, QK. What you need to do is you need to get rid of it. Okay, you need to get rid of it because remember the goal is to get a general transition graph that looks like this. Okay, so that's your goal. And to do that, you need to take this guy and essentially try to remove it. You want to remove QK, but you want to preserve all of the transitions that exist. So to do that, you essentially just need to add on to your initial regular expression, to your initial general transition graph. So what I mean by that is you need to essentially take all of the transitions that go through QK. You need to place them on existing edges. So for instance, if I'm in QI and I want to stay in QI, I can either take this this kind of transition RII, go back to myself, or the other thing I could do is I could go to QK with RIK, right? And then stay in QK a couple of times, right? Just chill there, RKK star. And then from QK, I can go back to QI with RKI, okay? And so this transition that I just added here accounts for the kind of using QK as an intermediate state. It's kind of, if you're taking the long way, QK is the midpoint in the long way. And so to eliminate it, you're just going to list the other way, so the alternative way of going from QI to itself, okay? And then you can essentially you repeat the same thing for all of the pairs of kind of transitions. So for instance, you have the same thing to go from QJ to itself. You can either use RJJ, or you can go to QK with, or you can go to QK with RJK, and then stay in QK a couple of times, right, for for a few transitions, and then go back to QJ with RKJ, right? And so essentially you repeat the process. You can do the same thing to go from QI to QJ. You can use QK as an intermediary, and the same thing the same thing can be said for going from QJ back to QI. Okay, and so then you get a more complicated general transition graph where you have alternative kind of routes. Okay, and because you've listed all the alternative routes, it's no longer necessary to have the QK there, so you can just eliminate it. You can eliminate all of its incident edges, and then you get this simplified general transition graph. And now at this point, you can just use the formula that we gave here, and then you get the sort of regular expression for that general transition graph. Okay, whoops. Okay, sorry about that. So then in general, the process is you take an intermediate state, all right, and for each of those intermediate states, you repeat the same process here, where you take all of the paths through that state, and you list all of the possible kind of transitions. And so then by listing all the possible transitions, you can delete that state. Okay. And so you repeat that for every single intermediate state until you get a single initial state and a single final state. All right. Okay, so that's probably very theoretical for you. Let me try to give you an example to make this a bit clearer. So you have the following NFA, and you want to convert it to a regular expression. So how are you going to do that? Well, the first thing is you need to take this guy and convert it to a general transition graph. And remember, the only difference between this and a general transition graph is your edges are labeled with regular expressions. So the only thing I'm going to do is just this a comma b, I'm going to replace it with a plus b. Okay, that's the only thing I'm going to do, right? Because there's nothing else that's really complicated here. I know that I already have, so I have a single final state and a single initial state, right? So I don't really need to do anything in my pre-processing. So I can just jump into the algorithm and start removing intermediate states. So the first intermediate state that I'm going to want to remove is this guy here. I'm going to want to remove 2. And remember, to do that, I need to account for all of the transitions that go through 2, right? Oh, God. Okay, sorry about that. Let me just turn my phone off. Sorry, guys. All right, sorry about that. That's very embarrassing. Okay, so what was I saying? Yeah, so you need to take this this intermediate state 2, and you need to get rid of it. And to do that, you need to essentially list all of the transitions that go through it. Okay, so what are the transitions that go through it? Well, if you start at 4, you can go through 2 to go to 3, right? And so to do that, what you would need to do, so to go directly from 4 to 3, you could read a B, right? You would read a B and then read a bunch of B's here. So with a B star here, and then go from 2 to 3 with an A, right? So this direct link that I just put is essentially just saying if 2 wasn't there, then what the transition would look like from 4 to 3 would be B star A, okay? And then the same thing can be said for going from 1 to 3 directly. So to go from 1 to 3 directly, you read an A or a B, and then you can read a bunch of B's, and then read an A. Okay, And so if I list this transition and this transition, all right, then I've accounted for all of the transitions that go through 2. So now I can get rid of 2. Can get rid of this incident edge, this edge, this edge, this edge. And so I get a simplified general transition graph where my edges here have accounted for removing the intermediate state. Okay, so hopefully that's clear. I know the interruptions with the phone probably made it a bit less clear. So again, you're going to want to repeat this process because you have another intermediate state, right? So you want to get rid of this intermediate state, and to do that, you essentially need to say, okay, if I get rid of 4, what transition am I affecting, and how can I conserve that transition? So if I get rid of 4, I need to consider the transition from 1 to 4b and from 4 to 3b, b star a, right? So I need to conserve that transition. And so 4 is allowing me to go from 1 to 3. And so to go from 1 to 3, I can either take this direct link or use this kind of longer path with 4. So then if I get rid of 4, then I can just list that transition here. Okay, so then because I've accounted for that additional transition, I can get rid of my intermediate state here 4, and I can get rid of this edge and this edge. And so the final GTG that I get, the final general transition graph that I get, is this guy. And so now we can clearly see that the regular expression that corresponds to this graph is just this guy, and that's because any pattern, any string that has this pattern is going to go from 1 to 3, and 3 is a final state. So you can see that there's kind of a direct correspondence between going from a initial to a final state and from being a string that's going to be recognized through the regular expression. Okay, all right, so that was an example of the NFA to regular expression algorithm. So now an exercise for you where I promise there won't be any phone call interruptions. You're given a language here over the alphabet. So the alphabet is 0, 1. Okay, and you want to find the regular expression that denotes the language that contains strings over 0, 1, where there is an even number of zeros and an even number of ones. Okay, and just because I don't want you to go through the sake of kind of the process of finding a DFA, this is the DFA. So this is the DFA, which is very similar to an example that we did in tutorial 2. So it's essentially just putting the final state in a different place, essentially. Okay, so so maybe take, what time is it? Okay, maybe take 1.5 minutes to try to take this guy and convert it to a regular expression, and then we'll do the question together. Okay, so it's been kind of 1 minute and a half. So let's see if you guys were able to sort of start this exercise. So we have the following NFA. Well, in this case, it's a DFA, and we want to convert it to its equivalent regular expression. So in this case, in this very special case, my initial state, is the same as my final state. You're going to see that once we get to the sort of the most compact form, it's not really going to matter. It's just going to be actually a bit easier to get the final regular expression, okay? But so essentially, what we need to do is we need to take each of these intermediate states and remove them one by one, so that remove them and keep the transitions, so preserve the transitions. I don't want to lose any of the information that's given by my NFA. Okay, so I've already written, so I apologize for how messy this looks, but I've already written the kind of the exact same GTG, but kind of in pen. So now what I'm going to do, the first intermediate state that I want to get rid of is going to be this guy. So I'm going to want to get rid of 1, okay? So how do I do that? Well, if I get rid of 1, what are the transitions that I need to preserve? Well, the 1 is allowing me to do what? If I'm in 0 here, then I can go back to 0 by reading a 1 and then reading another 1. So in other words, the 1 is allowing me to have a self loop on my 0, which is going to be 1, 1. Okay. The other transition that this intermediate state is allowing me to have is if I'm in 3, I can go from 3 to 1 with 0, and then from 1 to 3 with another 0. So I can also have a self loop on 3 using 0, 0. That's another transition that this intermediate state is allowing. So let me just finish my train of thought, Nicolo, and I'll answer that question. The other transition that this intermediate state is allowing is it's acting as an intermediary between 0 and 3. So you can use 1 to go from 0 using a 1 and then to 3 using another 0. So using a 1, 0, you can go from 0 to 1. So that can be written directly here. Okay. And as well, if you want to go from 3 back to 1, then you could read a 0, right? You can read a 0 and then a 1. Okay. So now if you write all of those direct, links, direct transitions, then you can get rid of this intermediate state and these kind of incident edges. Okay. And so with respect to, doesn't matter that the final state is the same as the initial state, it's not really going to affect the procedure of the algorithm up until the end. So you're going to see at the end, instead of having something that looks like this, we're going to have, well, I'll show you, but we're going to have something that looks like this. And then it's actually super easy. If you have something like this, it's super easy to know what the regular expression is. It's just R star, right? Because you can go to the final state with any number of R's, okay? So this is just kind of a simplified, an easier problem than this guy. But the procedure remains the same where you're removing intermediate states. Okay, all right. So now, what I did after this was actually a mistake because it got really complicated. So what I'm going to do is now I'm going to remove this intermediate state. So I'm going to try to remove 2. Okay, so let me just write out first the transitions that I already have. I have 1, 1. I have 1, 0 to go to 3. Then to stay at 3, I have 0, 0. Then to go back to my initial state, I have 0, 1. Okay, so Now, if I, what is this transition, what are the transitions that are allowed to go through 2? Well, if I'm in 0, I can go back to myself either with 1, 1, or I can use 0 and then 0. Okay, so now I have 2 possibilities for my self loop for my initial state. Either I can read 2 1s and and then I stay at the same place, or I can read 2 0s and I stay at the same place. Okay. The same thing can be said for 3. So for 3, if I read a 1, I go to 2, and if I read another 2, I go back to 3. So there's another self loop. There's another pattern that gives you a self loop for 3, and that's going to be 1, 1. Okay. And then to go from, say, 3, so to go from 3 to 0, my initial state, either I can go kind of directly with 0, 1, right? So this is my direct link. Or I can use kind of the longer path through 2. So I can go from 3 to 2 with a 1, and then from 2 to 0 with a 0. So that means to go from 3 to 0, I'm going to read a 1 or a 1 and a 0, right? So I have 2 options. I have 0, 0 and 1, or 1 and 0, okay? And then the same thing for going from this state, the initial final state, to the state 3. I can either go directly with a 1, 0, or I can go kind of the longer way through 0, reading a 0 to 2, and then reading a 1 to 3. Right? So now I get this guy. Okay. And now I can also get rid of this intermediate state. And the way I can do that is, well, my final state here, I can get to my final state either by self-looping with 1s, self-looping with 0s, or I can self-loop using kind of one of these paths, so either 1, 0 or 0, 1, then using this edge a bunch of times, and then going back to my final state with either 0, 1 or 1, 0. So how do I write that in terms of regular expressions? Well, either I have 1, 0 or 0, 1 to go to 3. Then I can stay in 3 with either of these pairs of symbols any number of times. And then I can go back to my final state with 0, 1 or 1, 0. Okay. And at that point, so at this point, as I was talking about with Nicolo, it's fairly easy to see what the regular expression is. If this is R, then the regular expression that's equivalent to this FA is going to be R star. Okay, so I'm not going to write it, but essentially you can just think of it as this guy is star. Okay. All right, so so that was a painful section, but hopefully it wasn't painful for you. And hopefully that's clear. So if there are any questions about this algorithm, please let me know. The main reason why this algorithm is shown to you is because in general, it's very difficult of thinking of a regular expression off the top of your head. If you're just given a problem like this, personally, I would not be able to find a regular expression directly. It's a lot easier to first look at an FA or a DFA and then convert it to a regular expression. Okay. And so this isn't in the slides, but to close off this section, this kind of leads us to a connection between regular languages and regular expressions. So we know that the set of regular, so this is something that you also saw in your lecture, but I just want to kind of reiterate the connection. The set of all regular languages, we know that a language is regular if and only if it can be accepted by a DFA. So the set of regular languages is equivalent to the set of languages L of M, where M is a DFA. And then we also saw that DFAs are equivalent to NFAs. So M is a DFA or an NFA. So in other words, if a machine accepts a language, if an FA accepts a language, then it's regular. And if a language is regular, then it has an FA that accepts it. But now we can actually say the same thing. We can say the same thing about L of R. the language denoted by the regular expression R. If a language is regular, so if a language is regular, then that means there exists a regular expression R that denotes it. And if there is a regular expression that denotes L, so if we have L of R, then this language is going to be regular, okay? So what this means is that now you have two ways of proving, well, actually you have three, but two ways of proving that L is regular. So the first way is you create an FAM such that L of M is equal to L. And now the second way, because we know that FAs are equivalent to regular expressions using this algorithm, the second way is you can create a regular expression R such that the language denoted by R is L. Okay, and so you can use these two methods, either creating a regular expression or creating an FA to show that a language is regular. And now we're going to actually see a third method, which is going to relate to grammars. Okay, so this is where I'm going to introduce grammars, in particular linear grammars and regular grammars. Okay, so what is a grammar? Well, let me give you the formal definition to refresh your memory. So a grammar is a four-tuple G, where G consists of a set of variables, a set of terminals. So here you can just think of the set of terminals as your alphabet. A single start variable. You can think of the start variable kind of like your initial state. Your initial state, but for grammars. And a set of production rules P. And P is very similar to kind of your transitions in your FA. Okay, and the production rules have the form X gives you Y, where X can be any sort of any combination of terminals and variables, except for lambda. So you can't have something like lambda gives you something. And then the right-hand side can literally be anything. So it can include lambda. It can have any combination of terminals and variables. So the right-hand side is kind of free for you to decide. So the only restriction is that X can't just be lambda, okay? So we can look at this first grammar here as an example. So we have the grammar G here with the variables SAB. So we usually use capital letters for these variables. We have the terminal symbols little a, little b, which can also kind of refer to just your alphabet. You have the start variable S. The start variable S is essentially the variable where you're going to start all your grammar productions, right? Where you're going to start generating any string. Any generation starts at S. And then P, this is your set of all the production rules. Okay. So, so far this really doesn't tell you much. What does a grammar do? Well, the main kind of use of grammars is to derive strings. So if using any number of production rules, you can start at X and derive a Y. Then you can also write X sort of with this superscript star gives you Y. So the idea is that a grammar can start with a certain left-hand side X and then generate a certain right-hand side Y using its production rules. Okay. So for example, using the previous grammar here with the production rules, you can say that the grammar G generates the string BBBA. So how does it do that? Well, any grammar generation, so any string that's generated by G, you always start with S, okay? And essentially the idea is you're just replacing. So production rules are just, you're taking the variable S and now you're going to replace it with S gives you A. So you're going to replace it with A, right? So now on my left-hand side, I have the variable A. So one of the production rules when I have A is I can replace it with BB, little b, big B, A. So that's what I'm going to have. Let me just say, I just have BB, BA, right? So S gives you A gives you BB, BA. And then you can replace B with a symbol, with a terminal, little b, using this production rule. And so here I see that S, through a set of production rules, can give me B cube A, right? So the idea in a grammar, so in general, in a grammar G, you want to list all of the strings that are generated by that grammar. And that set of strings is known as the language generated by G. So we also denote that L of G. So similarly to how L of M was the language accepted by the FAM, L of R was the language denoted by R, L of G is the set of all strings generated by your grammar. And so these strings are strings over your terminals such that they can be derived starting from the start variable S. Okay. So if we again sort of look at this running example here, where we have our grammar G and this set of production rules, what is the language generated by G? Well, you always want to start your derivations with S. Okay. So what's the shortest string that can be produced by G? Well, if you just replace S with lambda, then you're just going to get the symbol lambda, right? So that's the first string that can be generated by G. The other one is if instead of using lambda, I use A. So I replace S with capital A and then capital A with little a. I can also see that the grammar G generates the symbol A, right? So that's why I put it in L of G. And then again, if I start at S, I replace that with A, then I replace the A with BBBA, and then I replace this capital B with this production rule lambda. So really this is like BB lambda A, which we know is equal to BBA. So this is another string. So remember, a string is a list of symbols that are only from the terminals, right? So it's a string of terminals. So this string is also generated by G. So that's why it's in here. And as we saw before, B cube A can also be generated by G. So I'm not going to go through it because we just saw it, right? So that's essentially the high level idea of grammars. They allow you to generate strings, and in general, they generate languages. Okay. So another example here. What is the language generated by the following grammar? So in this case, so there shouldn't be an A here. That's a mistake. In this case, we only have two variables, S and B. So we see that starting at S, we can either replace that with a lambda or with capital B. So what is the smallest string that can be generated by G? Well, that's going to be S gives you lambda, right? So that's just going to be lambda. Then if you say, okay, I'm not going to use this lambda production rule anymore, I'm just going to straight away use this BB. Then you can say S gives you capital B little b, and then now what essentially is going on is you have options for what to replace the capital B with. Either you can replace it with two symbols B and then the variable B, or with a lambda. So in the first case, if I replace capital B with lambda, then I get lambda B, which is just B, right? So far the strings that are generated by G are lambda and B. But instead of replacing it with lambda, I could also replace it with this guy, right? With two B's and then a capital B, right? So then at this point, I would have BB capital BB. And then I could replace B with lambda. So I would get BB lambda B, and that would give me BBB, right? So then I would get BBB, right? And now hopefully you can start to see a pattern. The pattern is if I use, so I'm always going to start with a single B, right? If I go from S to B, I'm always going to start with a single B, so a single symbol B. And then every time I use the production rule here, I'm going to add 2. So I'm going to add an extra 2 B's. So that means that the strings that are generated by G are always going to be odd because they're always going to be 1 plus 2 times K, right? They're always going to be 1B plus K number of pairs of B's, right? So we see that in general, the language generated by G is going to be all of the kind of odd number of runs of B's plus the empty string lambda. So the language generated by G here is going to be the union of these two languages. All right. So hopefully this example is straightforward. Again, you can stop me if it's not. The next concept that I want to sort of make you familiar with is the idea of linear grammars. Okay, so there are two types of linear grammars that are of sort of importance. The first one is grammars G, which are left linear. Okay, so grammar G is left linear if all of the production rules look like you have a single variable on the left-hand side, and then on the right-hand side, you have a single variable on the right-hand side, followed by a string of terminals, okay? Or you have a single variable on the left, and then a string of terminals. So, for instance, if I had A gives me B, let's say AB, B, BBA, and BBA, this is an example of a left linear grammar. But if instead I had, for instance, A gives you, let's say ABA, then because this variable is in the middle, because it's not at the leftmost side, then this is not left linear. And also, if you had something like A gives you AB, this is not even linear, because a linear grammar is just one where on the right hand side you have a single variable. So in this case, this is not even linear. So of course it can't be left linear, right? And then similarly for right linear grammars, those are grammars where the production rules have a single variable on the left, and then on the right, the variable is at the rightmost of all the terminals, or you just don't have a variable. Okay, so for instance, if I had A gives you ABB or AB, this would be right linear. So of course, I'm forgetting, to say what the variables terminals are, just for the sake of kind of time. But in general, you should specify, if you want to be correct, you should specify what the variable is, what the terminals are, and so on. But here I'm just giving you the production rules. So in this case, this guy is right linear because, for instance, this production rule has a bunch of strings X and then a variable B. And another production rule that just has a bunch of strings that is just a set of a string of terminals. Okay. So that's a right linear grammar. And then the same thing can be said with kind of these examples here. This is also not right linear. And this again is not even linear, so it can't be right linear. Okay. And so finally, this leaves us, this kind of allows us to give the definition of a regular grammar. So a regular grammar G is a grammar that is either right linear or left linear. So notice this doesn't mean it's both, right? So for instance, if I have a production rule like S gives you say A, and B, and C, right? So these first two production rules are from a left linear grammar, but this one is from a right linear grammar. And so because this is neither right linear nor left linear, this is not a regular grammar, okay? Because it needs to be either right linear or left linear. It can't kind of have a mix of the two. So maybe a question for you is, for instance, if I have S gives you, let me think, A, or let's say AA, is this regular? So I have a feeling that no one's going to answer. So, oh, okay. Someone did answer. Okay, good. So, is this regular? No. Oh, wait, actually, someone's saying, okay, sorry. I was so surprised by the fact that someone answered, but so someone's saying no. Well, in fact, this is actually surprisingly, it is actually regular, because you can think of it as either being right linear. So it can either be right linear in the sense that you can say there's a lambda here, and then so you have some string here, and then a variable, and then some strings here, right? So it can either be qualified as right linear, or you can also say, oh, well, this is like a left linear grammar, because you could say a lambda, right? So then this would be a left linear grammar, okay? So this is not the same thing as this guy, where the kind of production rules are mixing. This guy is actually regular, because, for instance, you can play this trick with the lambda and say, oh, I can see that this could be a left linear grammar, or I can see that this could be a right linear grammar. Okay, but yes, thank you for answering. All right, so what time is it? Okay. So another example here, using the concept of kind of right linear grammars. We have a grammar G here, and we want to know what the language generated by G is here. Okay. Well, so if you kind of inspect, it's a bit easier to inspect regular grammars, because you always know where the variables are going to be. In this case, it's always going to be at the right. Okay, so it's easier to kind of see what's going on, and the reason for that is, if you start at S, well, you can stay at S. So notice I'm using the terms kind of like stay at S, kind of like an NFA. You can stay at S and produce kind of any form of a string over AB, right? So you can say maybe this. But because you want at some point to generate a string, and a string is a kind of a list of symbols, of terminals, well, at some point, what you need to do is you need to go from S to A, because A has the lambda, A has the empty string. And to do that, to go from S to A, you need to have the production rule ABA, okay? So that means at some point, I'm going to have some string W1 over AB, and then I'm going to have to read an AB, right? And then I can continue the process of saying, oh, I can have any string W2 over AB, because when I'm at A, I can either give myself an A or a B, and I can have any kind of permutation or combination of those. And then at some point, I'm going to end up with just replacing this. So maybe at this point, I have some string W2, and then I'm using the production rule BA, right? So then I can continue until I have two strings, let's say W, A, B, V, where W and V are over AB star. Okay. So we see here that any string generated by G is going to have AB as a substring. All right. And so that's why the language generated by G here is the set of all strings over AB, where W contains AB as a substring. Okay. So another, just quickly, do I have? Not really, but just to show you, just to give you another kind of reason why this is happening, is you can kind of see this as a form of FA. So if you have your initial state, which is going to be your start variable, and you can essentially read an A and go back to S, or read a B and go back to S. So you can do that here. And then if you want to get to A, which has the lambda, so it's kind of like a final state, then you can go from S to A with AB. You can go from S to A with AB, and then at A you can read any other kind of string over AB. So this is kind of the idea, which I'm not sure if you've been shown this already, or if it's going to happen this week. But this is how you would essentially convert this grammar to an FA. Okay. So Alec, you read in the book that all regular grammars are linear. Yes. But not all linear grammars are regular. Not all linear grammars are, yes. We're going to see an example in the next slide. So that's actually a great question. So if you take the grammar G here, where you have, in this case, okay, there shouldn't be a variable S. In this case, you have a single variable S here, and you have production rules. S gives you ASB, and S gives you lambda. So this is a linear grammar. Why is it linear? Because it has a single variable on the right-hand side. Okay, so it's kind of like a linear equation where you have only x to the 1, kind of. So here, this is like having a single variable, right? So that's why it's linear, okay? So it's for sure linear. However, it's not going to be regular, okay? In the sense that this grammar G is not going to even produce a regular language, okay? So this is something that you're going to see this week when you're going to talk about non-regular languages. But it's going to, so if we look at a couple of strings here, it's going to be clear what the language generated by G here is. So I know that I can generate lambda, right? I know I can also generate AB by replacing S with ASB, and then by replacing S with lambda. And then again, I could, instead of replacing S with lambda, I could do the same thing. So here I would have the same number of A's as B's. So I would have the same number of A's on the left as B's on the right. And so in general, I would have S gives me sort of A n times S, and then B n times. Okay, and then at some point you could replace S with lambda. And so all of your strings are going to look like AN, BN, okay? And if the professor hasn't talked about this yet, AN, BN is one of the first languages that you're going to see that is going to be not regular. So this language is, so the language here, language AN, BN, is not regular, okay? So this is an example of a linear grammar that produces a non-regular language. But in general, for Alex's question refers to grammars in particular. So there's a difference between a regular grammar and a regular language. Here, this grammar is linear, but it is not regular. Okay, so yes, this grammar is not regular because it is neither left linear nor right linear. Okay, because if it was left linear, then it would need to look like S A B, and if it was right linear, it would need to look like something A B S. Okay, so this is an example of a linear grammar that is not regular. Okay, so I'm not sure if that answers the question, but hopefully it does. Okay, what time is it? Okay, so so maybe if you want, I don't know how many people are left. If you want, you can maybe take a minute to try to do this exercise. It's not that it's, well, I don't, well, we'll see. Okay, maybe take a minute, and for those of you who are left, we're going to look at the solution together. All right, so hopefully you had some time to think about it. So what's the idea in this question? Here, I want all of the strings over AB where the length of AB, the length of that string, sorry, is even, right? So what is that going to look like? Well, this is kind of similar to the regular expression idea or intuition, in that your string W is going to be a sequence of pairs of elements, right? So you can think of each of these buckets as pairs of elements. And those pairs are either going to be AA, AB, BA, or BB, right? So once you generate one of these pairs, then you can move on to the next one. Or you can stop, with a lambda, okay? So you can stop the generation with a lambda, or you can continue it, with another kind of set of pairs. So if you start at S, right? Suppose you're starting here, then you can either generate AA, AB, BA, BB, or let me put ors here. Or you can just stop with a lambda. So you can actually immediately stop, right? Because a lambda has length 0, and that's clearly even, right? So you can create bins that have kind of these forms, and then once you create a bin with one of those pairs of elements, then you can start over the process for the next bin. And so to do that, you can just put another variable s after your pairs of elements, and you can do that for each one. Okay, and so writing G as s, the set of variables s, the set of terminals AB, the start variable is s, and the production rules P are here. And then all of this, so this guy gives me a grammar G such that L of G equals L, right? So that I don't think that was too bad, but if it was, don't hesitate to stop me. All right, so I know I'm going over the time. So these two questions were nice though, but okay, so let me just quickly let me just try to say these quickly. I'll just give you the answers. So this point was just saying that if you have a language L which is regular, then there exists a regular grammar G. So there exists a regular grammar G such that L of G, such that the grammar generates the regular language. Okay, and sort of vice versa. If you have a regular grammar, then every regular grammar generates a regular language, and every regular language can be generated by a regular grammar. Okay, so it's the same idea with FAs and with regular expressions. Okay, and lastly, these two exercises, which I thought were nice. So the first one here was kind of already answered. Well, actually, no, it wasn't. It states that there are non-regular grammars. So for instance, grammars that are not left linear and not right linear that generate regular languages. So is this true or false? Well, this is one of the tricky questions that people sometimes ask. A grammar doesn't need to be a regular to generate a regular language. Okay? So why? Because for instance, if I have S gives you AB, so this is not linear. So for sure, the grammar itself is not regular. And then if I say A gives me little a and B gives me little b, well then I know, so if this is my grammar G, I know that L of G is going to be just AB, right? Why? Because if I have S and I replace that with AB, then I replace A with little a, and then I replace B with little b. And this is the only possible derivation, the only possible terminal string that you can get from G. And so L of G is finite, so it must be regular. However, the grammar here is not regular. And so there are non-regular grammars that can generate regular languages. So this is actually true. All right. And then what grammars generate sigma star, the empty set, and the language containing lambda? If sigma is sigma is the alphabet AB. Well, so I'm going to leave these two for you to think about. I mean, the solution is in the next slide, but the one that I want to show you is a grammar G such that L of G is the empty set. So what kind of grammar G can do this? Well, there's actually a fairly easy one that you could write, which would just be S gives you S, okay? And the reason why this generates the empty string is because if you start at your start variable S, the only production rule you can use is S gives you S. And then essentially you can just repeat that for infinity, and you're essentially never going to get W as a string of terminals, right? You're never going to get a string of terminals. And so essentially what you can think of is you can think of the grammar never generating any terminal strings. And so if it does that, then the language that it generates is empty. So that's why in this case, L of G is the empty set, right? So for these two guys, I mean, they're fairly straightforward. For this one, you would just say your production rule gives you lambda. And for this guy, you would just say your production rule either gives you A and then you start over. So your production rule either gives you A and you start over, a B and you start over, or you can just stop. So yeah, I said I'd leave them as homework, but I left them there. All right. So yeah, so I think that's it. Yes. Okay. So yeah, so that concludes this tutorial. I'm sorry about the phone call at the beginning. It was very embarrassing. I'll make sure that doesn't happen again. So yeah, so if there are any questions, I'll maybe wait 30 seconds. Okay, so it doesn't look like there's any questions. So all right, so that's it for me, guys. Yeah, so again, sorry about the distraction at the beginning, and good luck in your quiz. Good luck in your assignments. Shoot us an email if you have any trouble with anything. And yeah, have a great week. All right, take care, guys.